Welcome to this explainer. Today we're going to take a nice, calm look at a really fundamental concept in computer science. We're talking about how computers actually start to understand the code we write. No rushed college lecture here, no pressure, just you, me, and some simple concepts to help us decode the amazing world of compiler construction. Let's get right into it. So how does a computer actually read your code? Well, think about how you read a book. You completely rely on spaces, punctuation, and paragraphs to make sense of the letters, right? Now imagine trying to read a book where all of that formatting is just gone. You're just staring at a massive, unbroken wall of letters. It's kind of a nightmare. But that chaotic, endless string of characters is exactly what a computer sees when it first looks at your source code. It has literally no idea what a keyword is or where a math equation starts and stops. It just sees raw, unformatted noise. So before any real translation can even begin, something has to step in and bring order to all that chaos. Look at the left side here. That's a raw, messy string of keystrokes. But on the right, you see how we actually need to understand it as distinct, meaningful words and symbols. The command printf, the opening parenthesis, the text string total equals %d, the comma, and finally the variable score. Something out there has to group that raw, jumbled input into those neat, organized little packages. Which brings us to section 1, from characters to tokens, sorting the chaos. Let's see how we actually break down this overwhelming complexity into manageable pieces. Now, this illustrates the whole multi-phase journey of a compiler. It looks like a lot, I know, but take a deep breath. We are entirely ignoring almost all of this today. We're only focusing on the very first step right at the top, the scanner. The scanner is basically our gatekeeper. Its entire reason for existing is to read the raw text and do that exact grouping we just talked about. It makes the rest of the compiler's job possible. To do this beautifully, the scanner looks for something called a lexeme. And hey, don't let the fancy word intimidate you. A lexeme is really just the raw text you typed that naturally belongs together, like the letters printf forming the word printx, or maybe a few digits that form the number 42. It's just the literal sequence of characters in your code that makes up a single logical unit. Once our scanner isolates a lexeme, it does something super important. It categorizes it into a token. You can think of a token as a safe, abstract label. The scanner looks at the lexeme printf and goes, yep, this is an identifier. It looks at 42 and says, okay, this belongs to the number category. By converting those raw lexemes into categorized tokens, the scanner gives the rest of the system a clean, predictable language to work with, completely hiding the messy reality of what you originally typed. Moving right along to section 2, meet lex, the generator. This is your translator's assistant. Now, you absolutely could sit down and write a scanner by hand. You could write hundreds of lines of C code, tracking every single character, managing memory buffers. But why do that tedious manual labor when we have a brilliantly helpful tool named Lex? Lex is a program that automatically generates your scanner for you. Instead of writing low-level code, you just hand Lex some high-level patterns, which we call regular expressions. You just tell it, hey Lex, anytime you see a sequence of digits, call it a number, and Lex does all the heavy lifting for you. The workflow here is beautifully simple. First, you write a basic text file, usually ending in .l, that holds your regular expression patterns. Second, you feed that file right into the Lex compiler. And third, Lex gracefully spits out a brand new file, usually named lex.yy.c. And this isn't just a text file, it's a complete, highly optimized, ready-to-work C program that acts perfectly as your scanner. You just compile it and boom, you're good to go. Okay, on to section 3, the 3-part Lex structure, a simple architecture. What's really cool about Lex is how beautifully organized it forces you to be. Every Lex file has a very clean 3-part harmony, separated by double % signs. You start at the top with declarations. That's your basic setup, variables, and C libraries. Then you step into the real heart of the file, the translation rules, where the pattern matching actually happens. And finally, you wrap up with auxiliary functions, just any extra C routines you might need to support your code. It's perfectly designed to keep your code and your mind totally clear. Inside those translation rules, the syntax is wonderfully minimal. Lex just looks for a pair, a pattern, followed by an action wrapped in curly braces. The pattern is your regular expression. If Lex finds a match in the text, it calmly executes the C code you dropped into the action block. So, if your pattern looks for the letters IF, your action might just be to return the token IF to the parser. just simple cause and effect. Let's dive into Section 4, Resolving Pattern Conflicts, Making Peaceful Decisions.
Sometimes code gets a little ambiguous. What if a chunk of text could technically match more than one of your patterns? Well, Lex doesn't panic. It uses 2 golden rules to make a calm, deterministic decision. First, it always prefers the longest possible match. So if you have a rule for less than and a rule for less than or equal to, and it sees a less than followed by an equals, it grabs both characters because that's the longest valid match. Second, if there's a total tie, like the word if matching both a keyword rule and a general identifier rule, Lex just defers to whichever rule you listed first in your file. It's totally peaceful, no fuss.
But wait, what if Lex needs a little more context? Sometimes, to know what a word actually is, you have to peek ahead at the characters coming up next without actually consuming them yet. For that, Lex gives us the look-ahead operator, which is just a /. It lets Lex gently peek ahead in the text stream, figure out the context, make its decision, and then politely return those extra characters right back to the input stream for the next round. Pretty clever, right?
And that brings us to Section 5, your practical takeaway, finding order from chaos.
You know, when you open a big compiler textbook, all those parsing trees and automata can seem deeply intimidating at first glance. But here's the thing to remember. Tools like Lex were built by programmers for programmers purely to make our lives easier. As the classic compiler's textbook says, the Lexical-Analyzer insulates a parser from the Lexian representation of tokens. I absolutely love that word, insulates. By stripping out the distracting white space, quietly deleting the comments, and neatly packaging the raw text into abstract tokens, Lex acts as a shield. It takes on the messy details so the rest of your program can just focus entirely on the big picture. And this idea extends way beyond just writing compilers. Lex is really just a system for recognizing patterns and creating order out of noise. So next time you're staring at a massive, chaotic spreadsheet or a giant wall of messy text, ask yourself, how might you build a few simple rules to transform all that noise into beautifully organized, meaningful data? Thanks for hanging out and taking this quiet time to explore with me today. Catch you next time.